Hello, everybody. My name is Ippokratis Pandis, and I work for Amazon. And today I'm going to talk to you about the world's new oil, data. In particular, I'm going to talk to you about data analytics, which is a very broad term, but in general consists of the processes of collecting data, storing them, and analyzing them in order to drive our day-to-day business and our operations. And it has never been easier in this time and day to collect data. We have the mobile phones, we have the click streams, we have the IoT sensors that continues to generate data, and the rate at which data gets generated increases over time. And it has never been easier, cheaper, and more secure to store the data. We have these disks in the cloud that it costs approximately $20 per month to store the data permanently in the cloud. Or we even have these tapes in the cloud that it costs approximately $1 per terabyte per month to store your data. But when it comes to analyzing the data, a lot of challenges arise. The shape of the data is changing. We have structured data, semi-structured, unstructured data. The velocity at which the data arrives has increased. The requirements about concurrency, about scalability are ever demanding, then they are increasing. And always there is a big responsibility to keep the data secure and make it easy for customers to go and use them to run their analytics on. Because of all these challenges in the sector, in the industry, people have been talking about the dark data problem. What it means with this term is that they are talking about an ever-increasing gap between the amount of data that gets generated and collected and stored in our systems and the amount of data we use for our day-to-day business decisions. There is almost an exponential growth in the amount of data we generate and store, and almost a linear increase in the amount of data we typically use for our day-to-day business decisions. And because of that, Amazon has seen this issue, and back in 2013, they launched the first cloud data warehouse, Amazon Redshift. Amazon Redshift is a very popular product, and in particular, at this time, we have tens of thousands of customers analyzing exabytes of data daily across the global AWS infrastructure that consists of 25 regions and 81 availability zones. It is safe to say that for today, our systems have already processed over an exabyte of data. That is a big data problem. This talk is about Amazon Redshift. And in particular, what we are going to talk about is we're going to talk about the evolution of the system from 2013 when we launched the service to where we are today, how the product has evolved over time. That was driven primarily by the needs of our customers. The evolution of Redshift is centered around four big work streams. The first and the most important is obviously security and availability. Our customers trust us to store and manage their data. So we absolutely need to make sure that the data is safe with us, and we provide a high available service to our customers. I'm not going to talk a lot about security and availability, but I'm going to jump to the next area where we are focusing a lot of our efforts, which is performance and elasticity. Before talking about performance and elasticity, let's first get a feeling of what is Amazon Redshift. How does this system look like? Amazon Redshift is a parallel data warehouse which consists of a compute layer and a storage layer. The compute layer, a Redshift compute cluster, consists of two types of nodes. There is the leader node, which is the entrance to the system. So customers connect to a leader, which is an endpoint for the customers to go and submit their jobs. And a bunch of compute nodes that are the workhorses. They do the work to execute the jobs that they have been asked to do. The data lives in a disaggregated storage layer, which we call the Redshift managed storage, and it is stored in a pure columnar format because this is kind of the optimal when it comes to running analytical workloads. So when a request comes into the system, we parse it, we try to make some smart decisions of how to execute this request. We take a cost-based decision about the shape of this query, and then we generate a query execution plan, which we then go and generate a highly tuned C++ code that corresponds to this distributed query execution plan. And when we do that, then we take this highly optimized C++ code, we compile it, and we send it down to the compute nodes to execute this request. The execution nodes go and scan the data. They use all sorts of tricks in order to make this processing as fast as possible. We used vectorized execution, and we have encodings that are friendly for vectorized execution, and we managed to process the data as fast as we can. There is always an appetite for higher performance. Customers want to execute their workloads as fast as they can. And in the way we are dealing with this challenge is that we are continuously look at the fleet that we are running, and we try to identify areas of improvement. And this is a never-stopping process. So in this graph, I am plotting the execution time of running industry benchmark, the cloud data warehouse benchmark that it is modeled after TPCDS. And I'm plotting the throughput, the performance of Redshift when it was running this benchmark over a period of 6 months. The way we improved this performance, the performance of Redshift running this workload, it was a very iterative process. We were looking at the telemetry, we were seeing where the time goes, and then we were going and fixing these issues. We were optimizing our code paths in order to make this workload run as fast as we can. And this is the beauty of the cloud. Our customers, they connect to the same endpoint, they have to do nothing in their application, and just the system just becomes faster over as the time passes. With a continuous focus on performance, we actually are managing to be ahead of the pack when it comes to price and performance. In this graph, this is a graph I took from a blog post we published at last Reinvent. We compare Redshift in price performance against a set of popular cloud data warehouses. And you can see that Redshift achieves between 1.2 to up to 3.8 times better price performance. So Redshift is a very fast system. What it is even more impressive is the scalability of the system. In this graph, I am plotting the throughput, the latency of Redshift in order that it takes to execute the cloud data warehouse benchmark model after TPCDS. As we increase both the amount of data that we are using for this benchmark, as well as the hardware we use to run this benchmark. And you can see that the amount of time it took for a 4-node system to run this 10 terabyte data set, it took pretty much the same amount of time as if 100 nodes were processing a petabyte of the same workload. So this linear almost scalability between 10 terabytes and 2 petabytes, 2 orders of magnitude more data, where the time it took was the same. It is a very welcoming property of the system, since customers can easily predict the performance of the system and also scale the systems as more work is coming and more workloads are being dumped into them. So when it comes to performance, Redshift has been doing very well. When we did that, our customers were delighted by the performance of the system, and the next challenge they threw at us was, we love Redshift, we love the performance of Redshift, but we would like to put more data into the system, and we would like to have more concurrent jobs executing in the system. And that's what we did. In particular, the big architectural change we did over the recent years was to create a disaggregated storage layer which can scale independently from the compute layer on top of it. In particular, we built the Redshift managed storage, which can scale up to tens of petabytes of data per database. This addressed the issues in terms of storage elasticity. When it comes to compute elasticity, we focused a lot of our efforts into achieving both scale up and scale down elasticity on the compute layer, as well as scale out. What do I mean by that? We added the ability to elastically change the size of an individual Redshift cluster in a matter of minutes by adding or removing compute nodes from this compute cluster. In addition to that, we added the ability to scale out, to auto-scale when the amount of jobs that it has been submitted to the system is too much, the system is clogged, it is doing work, and it needs some extra help. We added the ability to auto-scale, bring other Redshift clusters, attach these Redshift clusters on the main Redshift cluster, and route some jobs into this additional Redshift cluster in order to make sure that there is no waiting time and the throughput of the system increases along the way. And by doing so, we were able to get the ability to linearly scale the concurrency of the system, keeping also the latency of the individual queries low. In this graph, what I'm going to show you is the capabilities of Redshift to scale linearly each throughput. In particular, what I'm doing, I'm plotting the throughput of a 4-node DC2-8XL Redshift cluster when it is running the cloud data warehouse benchmark modeled after TPCTS, as an increasing number of concurrent users submit jobs with zero think time. Back in January 2019, the absolute maximum throughput a customer could get when it was running this workload was around 200 queries per hour when 5 concurrent users were submitting jobs. We started working in this area, and by April we were able to serve over 1,000 concurrent queries per hour by 50 or 60 concurrent users. By August we were reached 7,000 queries per hour by 180 concurrent users. And by November of the same year, we were able to run up to 220 concurrent users submitting queries with zero think time and achieving over 12,000 queries per hour in this workload. And because we have 220 users submitting queries with zero think time, this emulates a realistic scenario where thousands of concurrent users are submitting jobs. This type of scalability, going from 200 queries per hour to 12,000 queries per hour without having to do any change in the application layer, it is quite astonishing. It is a very nice property. And again, the customers did not have to do anything. We improved our systems on the back end, and we were able to provide over 60x improvement in concurrency. And we did not stop there. We have this ability now to scale up, scale down an individual endpoint and scale it out to multiple concurrent clusters from the same endpoint. But our customers said, okay, we would like also to have some isolation. I would like to spin up my own endpoint and being able to process the data that this centralized data warehouse is processing, has been generating. And that's what we did. We went and built a feature that it is called data sharing, which allows customers to spin up their own independent environments, their independent Redshift clusters, and access the transactionally live, consistent data from a main cluster that it is generating and curating a data set. So now you not only can scale up, scale down an individual compute endpoint, as well as scale it out to multiple clusters, but you can also pop up in isolated compute environments to do your job, to do your analysis. So by doing all this work, we were able to address requirements from our customers when it comes to performance and elasticity. Our customers came back and said, we love the performance, we love the elasticity of the system, but we would like to make Redshift available to less skilled individuals. We don't want to have database administrators managing the system. And that's what we did. We invested on autonomics. We tried to remove the decisions that need to be taken by an individual operator. So in the next few slides, I'm going to talk about how we use machine learning to improve both the health of the system as well as the performance. Machine learning is a very powerful tool that automates many difficult tasks that would normally have to be taken care of by an operator manually. As I told you in the beginning, Redshift is a very big enterprise. We have tens of thousands of customers in 25 launched regions across the globe in 81 availability zones. When you are running such an operation, it is very important to make sure that the system is healthy. And it is very easy or relatively easy to detect errors that it is a failed error, something that is operating and immediately all of a sudden stops working. You ask it, are you alive? You don't hear a response. You know that it is dead. You go and replace it, you remediate, and you are good to go. But even more challenging, it is when you have gray errors. Think about a network card that it is not very well attached to the hardware. Or think about a top-of-the-line rack that it is dropping packets along the way. These types of errors that it's not here nor there are very difficult to detect. So we invested a lot of our energy in trying to detect this type of outliers on live systems and with confidence say that something doesn't look good here and let's proceed with remediating function. That goes and improves the health and the operational health of our service. Then let's get into the database itself, the data warehouse itself. There, we invested a lot in automating all the cumbersome maintenance operations. So the way it works is that the system monitors the workload, see what the customer is doing, and at times of, say, low activity, or depending on the priority of the maintenance operation that needs to happen, Redshift takes over and performs this maintenance operation either in the background or while another workload is running. And we have automated a bunch of the cumbersome maintenance operations. So when we see that a table needs to be analyzed or needs to be vacuumed and needs to be sorted or cleaned up in terms of deleted rows, we do that. We take the option of performing this maintenance operation. A very interesting feature that we launched last year was that we launched a new type of table in Redshift that we will call Auto. What happens there is that the customer declares a table in the database and says, Redshift, you go ahead and you are responsible for that. You make all the decisions about how I'm going to deal with this table. This is the schema, you take care of that. And that's what we do. We build algorithms that try to find the optimal physical design of this table. We pop this recommendation up to the customer as part of the console. But in addition to that, for tables that have been declared as auto tables, we go ahead and do this change when we are feeling confident that they are making this change in the physical design of the table would have improved the performance of the overall workload. And it is quite impressive how this thing works. In this graph, I am plotting the time it took to run the cloud data warehouse benchmark modeled after TPCTS on an array-3 16XL, 5-node array-3 16XL cluster. And when the customer did not do anything smart, they just defined a bunch of tables, loaded the data, and start running the workload. Within 48 hours, within 2 days, where it was taking 100 minutes to run this workload, it went down to 60 minutes without the customer having to do anything. We just detected the patterns, we did some changes in the tables, the physical design of the table, and the workload ran almost twice as fast. So those are kind of the type of autonomics we had to build in order to make the performance of the system better, the health of the system better, without the customer having to have deep knowledge of the system and without having to spend a lot of resources in administering it. The next area, the fourth area where we put a lot of energy, is around integrating with the entire AWS ecosystem. As you probably know, AWS is a part of pretty much any enterprise's operation. Customers use Amazon S3 to store exabytes of data. We have operational databases, key value stores, machine learning tools. And customers came to us and said, we really like the data warehousing capabilities that we are providing in Redshift, but we would like also to combine these capabilities with and use them in order to process not only the data in the warehouse, but also outside in the AWS ecosystem. And that's what we did. The first thing we did was to build a capability of Redshift called Amazon Redshift Spectrum that allows Redshift to access not only the data that it is stored inside the data warehouse, but also to process analyze data that are stored in Amazon S3 in open file formats such as Parquet and ORC. By building Spectrum, now the customers have the ability to join the data in the data lake in Amazon S3 with their data in their data warehouse, directing to an architecture that it is often referred to as a lake house architecture. You have the data warehouse, you have your data lake, you put them together, you have a lake house. But that was not enough, because then customers told us, you know what, we have Amazon Aurora, we love your operational database. We would like to be able to also use this data in our day-to-day analysis. And that's what we did. We built a capability called federated query that can go and query these operational databases that live on Amazon RDS and Amazon Aurora. So that now the customers have the ability to join the data in S3, in the warehouse, as well as in the operational database. And because oftentimes customers, they want to move the data from their operational front to the warehouse for even more efficient analysis, we built also the ability to have incrementally maintained materialized views in the lake, in the AWS ecosystem. We have already announced a product called Glue Elastic Views that can take data that you can use in AWS. And for example, you can be loading your data in a key value store like DynamoDB, and the data to be reflected, be mirrored into a warehouse in an incremental fashion. So now our customers have the ability to process the data in the lake, in the warehouse, and in the operational databases. The next thing they asked us was, we really like this, but we have machine learning. Machine learning is something that we want to use for our day-to-day business decisions. And before integrating with SageMaker, which is Amazon suite of machine learning products, the customers had to do a very cumbersome operation, which was to export the data from the warehouse and use them, say, using SageMaker. And instead of that, what we did, we allowed the ability to train models from within the database, from the SQL surface to go and create a model using SageMaker, and as well as use the model as a function in order to run inference. So customers within SQL, they can run typical data warehousing reporting, but also they can combine it with machine learning, doing inference as part of their SQL queries. And because we wanted to be generic enough, we also integrated with AWS Lambda. So customers can run almost arbitrary amount code functions and be triggering Lambda functions while they're within their SQL, within Redshift. And what we end up doing is that now customers with Redshift, they can use the right tool for the job. And Redshift becomes a one-stop solution for all their analytical needs. So that was my talk. I walked you through from 2013 to 2021, and we saw the evolution of Redshift. Redshift is a very popular data warehouse, tens of thousands of customers using exabytes of data daily. We're very focused on performance and scalability. We have customers can have thousands of concurrent users using Redshift and to analyze tens of petabytes of data per database. We are trying to make the life of our customers very easy by building a lot of autonomics, a lot of smartness in the system to reduce the maintenance overhead of the system. And we are integrated with the very rich and broad AWS ecosystem. And as we like to say at Amazon, it is still day one. There is a lot of innovation that can happen in the space, and we are excited for the future. And that was my talk. Thank you. If there are any questions, I would be happy to answer. My email is ippo@amazon.com if anybody wants to contact me offline. Thank you very much.